Hello friends, welcome back to the CSC Guide. Today we are going to explore some advanced concepts in artificial intelligence, focusing on informed search strategies, search in complex environment, and adversarial search. We will cover greedy best first search, A-star search, heuristic functions, local search, optimization problems, and delve into adversarial search techniques like alpha-beta pruning and Monte Carlo tree search. So let's get started. First, let's discuss informed search strategies. Unlike uninformed search strategies, which explore the search space without any additional information, informed search strategies use heuristics to guide their search. Greedy best first search is an algorithm that selects the node that appears to be closest to the goal based on a heuristic function. The idea is to minimize the estimated cost to reach the goal from the current node. For example, imagine you are trying to find the shortest path on a map. Greedy best first search would look at the straight line distance to the destination and choose the path that seems to lead most directly to it. However, while this approach can be fast, it does not guarantee the shortest path. It can get stuck in local minima where it seems like a path is the best function, but there is a better path that's not immediately obvious. Next, we have A-star search, which combines the strengths of both greedy best first search and uniform cost search. A-star uses a heuristic function to estimate the cost to reach the goal, but it also considers the cost to reach the current node. The formula of A-star is f of n is equal to g of n plus h of n, where f of n is the total estimated cost of the cheapest solution through node n, g of n is the cost to reach node n from the start, and h of n is the estimated cost from the node n to the goal. This means A star is both optimal and complete, provided that the heuristic is admissible, meaning it never overestimates the true cost. A star is widely used in pathfinding and graph traversal due to its efficiency and accuracy. Heuristic functions. Heuristic functions are crucial for informed search strategies. A heuristic is a way to estimate how close a state is to the goal. Good heuristics can significantly improve the efficiency of search algorithms. For example, in a chess game, a heuristic might evaluate the board position based on material advantage, peace, mobility, and control of the center. The better the heuristic, the more effectively the search algorithm can prune the search space and find optimal solutions. Now let's move on to the search in complex environments. This includes local search and optimization problems, as well as dealing with continuous spaces and non-deterministic actions. Local search. Local search algorithms operate by exploring the neighborhood of a current solution rather than the entire search space. They are particularly useful for optimization problems where the goal is to find the best solution among many. For instance, consider the traveling salesman problem, where you want to find the shortest route visiting a set of cities. A local search might start with a random route and then iteratively make small changes like swapping two cities to find a shorter route. Local search is efficient but can get stuck in local optima, which are solutions that are better than their neighbors but are not the best overall. Optimization problems. Optimization problems are a class of problems where the goal is to find the best solution according to some criteria. Local search is often used in these scenarios, especially when the search space is large and complex. Techniques like simulated annealing and genetic algorithms are popular for solving optimization problems. Simulated annealing mimics the cooling process of metals, allowing for occasional uphill moves to escape local optima, while genetic algorithms use principles of natural selection to evolve solutions over generations. Local search in continuous space. Local search can also be applied in continuous spaces where solutions are not discrete. For example, in a function optimization problem, you might want to find the maximum value of a function over a continuous range. Gradient descent is a particularly useful in training machine learning models where the goal is to minimize a loss function. However, it's important to note that gradient descent can also get stuck in local minima. So, techniques like momentum or adaptive learning rates are often employed to help navigate the search space more effectively. Next, let's talk about search in environments with non-deterministic actions. In many real-world scenarios, the outcome of an action may not be predictable. For example, in a game of chess, a player's move can lead to various responses from the opponent. To handle this uncertainty, we can use techniques like Markov decision processes, MDPs, or partially observable Markov decision processes. MDPs provide a framework for modeling decision making where outcomes are partly random and partly under the control of a decision maker. In POMDMS, partially observable Markov decision processes, the agent does not have complete information about the state of the environment, which adds another layer of complexity. These models are useful in robotics, automated planning, and other areas where uncertainty is a factor. Now let's shift our focus to adversarial search, which is crucial in scenarios where multiple agents compete against each other, such as in games. Here we want to make optimal decisions while considering the potential moves of an opponent. In adversarial settings, the goal is to maximize your chances of winning while minimizing the opponent's chances. This is often modeled using game trees, where each node represents a game state and edges represent possible moves. The minimax algorithm is a classic approach used in two-player games. It assumes that both players play optimally. The algorithm works by recursively evaluating the game tree, assigning values to terminal states based on the outcome, and propagating these values back up the tree to determine the best move for the current player. Heuristic alpha beta search. To improve the efficiency of the minimax algorithm, we can use alpha beta pruning. This technique reduces the number of nodes evaluated in the search tree by eliminating branches that won't affect the final decision. Alpha beta pruning maintains two values, alpha and beta, which represents the minimum score that the maximizing player is assured of and the maximum score that the minimizing player is assured of, respectively. If at any point the algorithm finds that the node's value is worse than the current alpha or beta, it can prune that branch, saving time and computational resources. This allows the algorithm to search deeper in the tree within the same time constraints, leading to a better decision making in complex games. Monte Carlo search tree. Finally, we have Monte Carlo tree search or MCTS, which is particularly effective in games with large search spaces like Go. MCTS uses random sampling of the search space to evaluate the potential outcomes of the moves. The algorithm consists of four main types: selection, expansion, simulation, and backpropagation. It builds a search tree incrementally, exploring the most promising moves based on random simulations. MCTS has gained popularity due to its success in various games, including AlphaGo, which famously defeated a world champion Go player. In summary, we have covered a range of topics in AI, including informed search strategies like greedy best first search and A-star search, the importance of heuristic functions, and how local search techniques can be applied to optimization problems and continuous spaces. We also discussed how to handle non-deterministic actions and explored adversarial search techniques, including minimax, alpha-beta pruning, and Monte Carlo search tree search. These concepts are fundamental in AI and have applications in various fields from game development to robotics and beyond. Thank you for joining me today. If you found this video informative, please give it a thumbs up, subscribe for more content, and leave your thoughts or questions in the comments below. See you next time.